In this lesson, you'll dive deep into the bandwidth requirements for training a model using federated learning. You'll understand how to reason about bandwidth usage of federated systems in theory and how to measure bandwidth consumption using Flower in practice. Let's have some fun. Let's revisit this animation from lesson 2. As you can see, there are many models going back and forth between the server and the clients. In the context of LLMs, where models get larger and larger, it's important to understand the bandwidth implications of this. We'll now walk through a formula that helps you to calculate the rough bandwidth requirements of a federated learning setup. To better understand the bandwidth usage of a federated learning system, we'll slowly walk through a formula that helps us to calculate approximate bandwidth usage of running such a system. We start by looking at the size of an individual model that we send to an individual client. To the size of the model that goes out, that we send out to that individual client, we add the size of the model that we receive back from that client. In some scenarios, those two sizes are not the same. Sometimes we send out full model parameters to a client, but then the client returns compressed gradients back. So the size of the update that we receive back from the client is smaller than the size of the model we sent out. Adding up the size of the model we sent out to the client and the size of the model update we receive back from the client gives us the bandwidth requirements for sending one model to one client and receiving the update back from that client. We multiply that by the cohort size, the total number of clients we have in our system. In some of the previous lessons, we had a diagram that showed 5 different clients. In that case, we would multiply that number by 5. We often don't select all of those clients during a single round. So we need to multiply it by the fraction of clients we select during each round. If we have 100 clients, but we only select 20% of those clients, we would multiply it by 0.2. Last, we multiply that number by the number of rounds we perform. So all of the previous steps gave us the bandwidth requirements for a single round of federated learning, and then we use that and multiply it by the total number of rounds we are about to perform. If the size of the model we send out and the size of the model we receive back from a client is the same, we can just take the model size times 2. This is the simplified formula for calculating bandwidth requirements in federated learning. Let's walk through an example. In course 2, Nick will cover federated LLM fine-tuning on private data. The language model that will be used in course 2 is Eleuther's Pythia 14M model, a language model with 14 million parameters. The size of this model is 53 megabytes. Following our simplified formula, we multiply this by 2 to get the bandwidth usage of sending the model to one client and then receiving the model back from that client. If we train this model across 2 clients, we multiply that number by 2. And because we have 2 clients, we'll select both of them during a single round. If we had, for example, a cohort size of 100, it would be reasonable to select only 50 of them during a single round of federated learning. In that case, we would set fraction selected to 0.5 instead of 1.0. Last, we multiply by the number of rounds of federated learning we do. In the lab, to not waste time, we'll only do a single round, so we set this to 1. This gives us a total bandwidth usage of 212 megabytes for a single round of federated learning. Let's jump into the lab to see if we're right. As usual, you start by importing utility functions and classes. You also import a client-side mod called parameters size mod. You'll use that mod to track on the client side the size of parameters transmitted. You first initialize a language model for causal language model using the Eleuther AI Pythia model with a size of 14 million parameters. This is indicated by the Pythia -14m string. The cached parameter specifies the directory where the downloaded model weights will be cached. The static method retrieves the model's parameters as a dictionary of tensors, and you call .values to get the actual values. The total size bytes variable calculates the total size of the model in bytes by summing the element sizes in bytes multiplied by the number of elements in each parameter tensor. The total size in bytes is then converted to megabytes and rounded down to the nearest integer. This gives us the model size of 53 megabytes we also used in the calculation example earlier. The Flower client is defined as in previous lessons. One difference is that we skip the actual training and evaluation parts, as we only want to compute the bandwidth. On the server side, you can track the size of models sent and received by creating a custom strategy. Our custom strategy is called bandwidth tracking fed averaging. It extends the federated averaging strategy you used in earlier lessons. In the aggregate fit method, for each client's result, it calculates the size of the received model update in megabytes and logs it. The model size is also appended to the bandwidth_sizes list. In configure fit, it calculates the size of the model that is going to be sent out to the clients in megabytes and logs it. The size of the model update with respect to the number of available clients is appended to the bandwidth sizes list. Last, you create the server app. The strategy sets fraction evaluate to 0 to disable client-side evaluation. The number of rounds is set to 1. It's sufficient to run this for 1 round, because in this setup, the bandwidth requirements do not change over consecutive rounds. Let's start your simulation as always. In the logs, you can see that the size of the model to be sent is 53 megabytes. Due to the client-side mod, you can also see the number of bytes that were transmitted, which is roughly equal to 53 megabytes. You also see that the server receives 2 models of size 53 megabytes. Last, we log the total bandwidth used by summing up all the elements in bandwidth_sizes. You see that in total 212 megabytes of bandwidth were used. This is exactly what you calculated when using the formula. Good job! In the lab, we've seen that even performing just a single round of federated learning can quickly eat up a lot of bandwidth. There are many ways to reduce bandwidth usage in federated learning. 2 categories of improvements are reducing the size of an individual update and also just communicating less. To reduce the size of an update, you can use, for example, sparsification and quantization. With top K sparsification, if the gradients to be communicated are below a certain threshold, then instead of communicating them, they would be communicated as 0. This can often be skipped and it therefore saves in communication costs. This is highly likely towards the end of the training, where more elements in the gradients will be small in magnitude. One other thing that you can do to reduce the size of an update is to apply quantization. There are many forms of quantization and they reduce the number of bits to represent scalars, which in turn reduces the size of updates exchanged between client and server. You can also leverage pre-trained models. In many settings, it's realistic to assume that a pre-trained model can be found that's useful for your particular application. Federated learning can then continue the training. In such cases, we might not need to train every single layer and only communicate the layers that are modified by the federated training. One other approach is to simply train longer locally before exchanging updates with the server. Instead of training just 1 local epoch, you could train 5 epochs before sending the updated model back to the server. Be aware that this could also prevent convergence. If the local model trains too many epochs, they diverge more and more, which can cause the aggregated model to become worse instead of better. Let's review lesson 5. We can calculate bandwidth requirements by summing up the size of the model that is outgoing and the model that is incoming. And we multiply that by the cohort size and the fraction of clients selected in each round. We also multiply that by the number of rounds to get the total bandwidth requirements for a single federated learning run. In a real-world implementation, we can measure bandwidth by using client-side mods in Flower and server-side strategies to measure the server-side and the client-side bandwidth requirements. We can also optimize bandwidth utilization by applying techniques such as sparsification or quantization, and by using pre-trained models not communicating all of the layers, or simply by applying more local training before exchanging model updates with the server.